Imagine you're about to embark on a long journey over the ocean, or perhaps across the prairie, it doesn't matter. A long journey that's going to take you a week, a month, perhaps a year, out of sight of land. You've got to figure out how you're going to determine how far you've gone. For all you know, you could fall off the edge of the earth. You need to know where you are. To deal with that, man in his ingenuity has invented these lines they call lines of longitude. Okay, let me explain what these are. Consider this earth. Picture this earth. I think you've seen it all before. No big deal. It's round. Now let's take another look at the perspective of the earth from the top, the North Pole, and look down again. And now we'll see again, it's another circle. That's what we'd expect. If we were to take that circle and then divide it into lines, how many, you say? Well, how about if we divide it into 360 degrees, just like the compass? These Babylonians did love their 360 degrees. So we can now divide the earth into these lines of longitude. Now, if you recall, each day is 24 hours long. So the earth rotates once every 24 hours. Therefore, every 24 hours, it turns a total of 360 degrees. So, if we were to take 360, divide it by 24, we would discover that the earth rotates 15 degrees every hour. Now that is important. As you know, sunrise can occur at different times, depending on whether it's summer or winter. The sunrise in August comes quite a bit earlier than the sunrise in December. Likewise, the sunset comes at different times. The sunset in August is quite a bit later than the sunset in December. Those two times are a little bit arbitrary, but midday is always the point at which the sun is directly above your head. And right now for us it comes more or less around noon, but we'll refer to midday. The midday sun is directly above you. So in order to determine time, people invented a thing called a sundial. Here are some images of sundials. The sundial is a very effective device for determining exactly when the sun is at its highest point. I'm going to be asking you to make a primitive sundial. What you're going to be doing is taking a board like this, drawing lines across it. First of all, one line across, I'll say, the bottom part, and then midway down that line you're going to draw a vertical line, so it looks like a great big T. Then, at the intersection of the two lines, you're going to drive in a nail or perhaps a screw. I'm going to be using a screw. I'm going to be asking you to build one of these, so we'll see how you do on that one. Now, if we take our primitive sundial outside on a sunny day, we may have to wait a little bit for that. We take it outside, and I line up the baseline, the east-west line, with a compass, the one we've already calibrated, or in my case I'm going to use my iPhone, just to make sure I've got my east-west line perfectly. And I'm going to look for the shadow of the sun, the shadow of the nail, as it casts on the sundial. I deliberately painted this one nice and white so we'd see it. As the sun comes up on the east, remember it rises in the east, as it comes up, it'll cast a shadow from the nail in a westward direction. As it sets in the west, it will cast a shadow in the eastward direction. But when the sun is directly above the sundial, the shadow it casts will be right over the the line I drew in the north south direction, the top part of that T. If all goes well, the value, this should occur at noon. But when we do this experiment, it's quite obvious that it does not occur at noon. Let me explain why. Let's consider sunrise in Prince Rupert. Whenever it happens, like this morning, I think it was around 5:30 in the morning. 5:30 in the morning, I saw the sun coming up. It was lovely. And an hour later, now 6:30, the sun's quite a bit higher in the sky. But at 6:30, someone out in the Pacific is enjoying the sunrise. It's only just reaching there. And this is because the Earth is rotating underneath the sun. And it's gone 15 degrees every hour. So if you were to look at the, again, view of the North Pole with all these lines coming off here, somebody's got to decide where the zero line is going to be. And for years, wars were fought over it. And finally, it was settled that the 0/360 degree line will be called the prime meridian, and it will pass through a little suburb of London called Greenwich. So we now refer to the time of sunrise, sunset, whatever it is, through Greenwich as Greenwich Mean Time. Now let's assume that we're sitting in Greenwich, England. Actually, I think it's Greenwich is landlocked, but assume there was water there. And the captain said, well, it's noon, let's cast off. And we're going to head west. Okay. The boat you're on, because it has to be a boat, you're going to be going out into the Atlantic. The boat you're on travels 15 degrees. Then the captain says, matey, what time is it? The matey looks at his watch. It's 12 o'clock. And he says, the captain says, nonsense, look where the sun is. It's not 12 o'clock for another hour. Aye, you're absolutely right. So what it was decided that's because the Earth has moved 15 degrees. So in order to compensate for this, what scientists have done, what everybody did, geographers I guess, is they said, let's change the clocks every 15 degrees or so, and let's create time zones that will allow for this 15 degree 1 hour shift. And that's why we came up with maps such as this one, a map of Canada's time zones.
Here we are. This is Prince Rupert, and around here, we're in the Pacific Standard Zone, the Pacific Time Zone, right here. If I want to call my mother, who lives in Ontario, my mother usually is ready for a phone call around 7 o'clock at night. So I will pick up the phone at 4 in the afternoon. When I pick up the phone at 4, it is now 5 o'clock in Alberta, 1 hour difference, 6 o'clock in Saskatchewan and Manitoba, and it's 7 o'clock in Ontario. That way, she gets to talk to me at a reasonable time. Now, if we look at the world map, we'll see this is where Greenwich is, right in here. And this red area right here is basically the zero time zone. Each one of these lines represents about 15 degrees. The lines aren't smooth. Notice how they're sort of irregular. This is for political convenience. Here I am in Prince Rupert, and I want to call London, England. So I've got to count the time zones. If I'm going to call, say, at 4 in the afternoon, instead of calling my mother, I'm going to call London. So therefore it would be 5 here, be 6 there, 7 there, 8, 9, 10, 11, 12, it would be midnight in England. There are 8 hours difference between the time zones.
Now I got my sundial built, and I sat around waiting and waiting for a break in the weather so I could take it out and test it. Then just this morning, the weather program said that we're going to have a sunny day. So I took my sundial outside, I lined it up with the vertical line, the north-south line, pointing towards the north. You'll see here I've put a compass down there to try to line it up. Notice on the compass that I've built in the declination, the arrow, the red arrow is pointing about 22 degrees to the right, and the main north-south line is straight parallel with the line I want. Then I thought I'd wait until about noon. Wouldn't you know, clouds came in. I got so frustrated, and I'm afraid what I've done is I've took the model inside and I've simulated what I'd expect to see using a flashlight, so forgive me that little indiscretion. The first image shows what the sundial would look like in the morning. Because the sun's rising on the east, you'd expect the shadow to be cast towards the west, like this. The next image shows what I think the sundial should look like when it's midday. And you see the shadow should be cast right along that north-south line. And then the last image shows what should happen when the sun is in the afternoon sky. It should cast a shadow to the east, like this last image. Okay? If I did this correctly, I would find that midday line occurred right at 12:40. Not 12 o'clock as one would expect, but 12:40. This is a little not surprising, but this is what we've got to work with.
Here's our timelines again. And this is Prince Rupert right here. And you'll notice this, the 120 degree line right there. And if we look at the date lines, we see that this is exactly 8 hours. It comes exactly 8 hours after Greenwich Mean Time. The Earth is rotated enough to, 120 degrees, and now this is when noon would be. But when we did our calculations with the sundial, we discovered that it wasn't noon at the right time. It was noon 40 minutes later. That's enough time for the Earth to rotate from there to there. So we know that every 60 minutes, the Earth rotates 15 degrees, from 120 to 135, every 15 minutes. Therefore, we can calculate that the Earth rotates 25 degrees in 1 minute. The way we can calculate that is to simply take 15 degrees, divide it by 60 minutes, number of minutes in an hour, and there's 0.25 degrees. That's how much the Earth rotates in 1 minute. Consequently, the highest point of the sun, if it occurs 40 minutes after noon, when it's noon at the 120th meridian, the Earth will have rotated 40 times 0.25 degrees. Now, I'll just clear this and make sure you know it's 40 times 0.25 degrees. The Earth has moved 10 degrees. Okay, so that means that the longitude of Prince Rupert is in fact 120 degrees, there's the 120, plus the 10 that it's moved since that is 10 degrees right there to there, which is not unreasonable. Remember, here's 135, and that would be another 5 degrees, so that's not unreasonable to go 10 degrees from there to there. So it gives us a longitude of 130 degrees. Now, if I look up the longitude of my house in Prince Rupert, we discover it's 130 degrees, right on, plus 20 minutes. Well, our sundial is certainly not accurate enough to go down to the minutes, then it's quite obvious that timing is going to be an issue when we have to calculate what the longitude is.
I hope you can see that to determine the longitude of your vessel, if you're assuming you're out at sea, requires a very good clock. You need to know exactly what time it is so you can calibrate with respect to Greenwich Mean Time. The problem is, prior to the 1700s, the only way you could really accurately measure time at sea was with an egg timer, an hourglass. So what mariners did is they had a crew member flip the egg timer every half hour or hour, depends on the size of the egg timer. I guess I should call it an hourglass. Flip it, and then when it's emptied, they flip it again. In order to keep track of how many times they flip it, every time they flipped the egg timer, they rang a bell, and that's where the bells on ships come from. 1 bell, 2 bells, 3 bells. And the ship then, up to 8 bells if I remember correctly, then the bells signify to the crew not only that the egg timer has been turned, but it also indicates when their watch starts, their shift. So seldom did they start at 9 and go to 5, they would have different watches. Okay, then there were accurate clocks that you could use on land. They were sort of wind-up clocks, but they had pendulum, or pendula. When the pendulum was swinging back and forth on land, not a problem. But if you took that clock out onto the ocean, and the ship was being tossed around by the waves, the pendulum was actually useless, and the clock would not demonstrate, or not show you the correct time. So the British Admiralty had a contest to see if people could build a very accurate clock to be used at sea. And in 1736, a man by the name of John Harrison, actually he collected, well, he won a prize for designing, building, and using a marine chronometer. Fancy name for a good clock. And it functions much the way as modern watches do. This is electric, but modern watches use a wind-up mechanism, a spring, that doesn't matter how you orient your watch, it still works. There's no pendulum in here. So, with the new chronometers, you were able to cross the large bodies of water and do a calculation for exactly what the longitude was. John Harrison won the prize for this when a ship left Portsmouth, and I believe it was 8 days later, it turned up in Jamaica, and the longitude calculation was so accurate it was within 1 nautical mile of the true position, and that was very, very, very accurate for those days. Nowadays, of course, we'd expect it to be that much more accurate, especially with Google Earth and stuff like that. But anyway, that's how they go about calculating longitude at sea. Now imagine you were a cartographer. A cartographer is a guy who draws maps. And you have before you a globe with all the continents and the oceans drawn on it. How on earth could you project that in a way that it could be seen on a two-dimensional map? Something you could roll up and put in your pocket or take out on the boat. You can't. You could take the globe, but it would be very difficult to use because you've got to blow everything up. Imagine a great big globe the size of, whatever, a room. So the problem we have is that if you take a look at the globe and draw on it all the continents, such as you would do, say, for an orange. Draw the continents and the land masses on an orange, and if you tried to get that image onto a piece of paper, it would be like peeling the orange and laying the orange down flat on the piece of paper. And you would have something that looks like this. This is the good Homolocene projection. Not very useful, but probably incredibly accurate. If we want to take a look at this, in a regular map, what we've got to do is we've got to make sure that all the longitudinal lines are nice and straight. So we've got to flatten out that orange, but we've got to also fill in all those gaps where the peel is broken away and there are big spaces. So what map drawers, cartographers have done, is they stretch everything above the equator, they stretch it out. And as a result, countries like Canada look somewhat triangular because you've had to fill in that empty space on the orange by stretching everything in between. Where the orange was, you stretch that. That creates a whole new map projection called a Mercator projection. If we look at a Mercator projection, we'll discover that the longitudinal lines are perfectly parallel. In order to explain or calculate for that little stretch, if you take a look at your topographical map again, you'll see on the calculation for the declination, on there is an indication that the top of the map is 1 degree different from the bottom. That accounts for the stretch factor. So the top scale of the map is a little bit different than the bottom. Okay. Now your assignment is to build a simple sundial such as I've built, and hopefully you're going to have some nice weather, some sunny weather, to take it outside and to determine exactly when the sun is at the middle of the day. And you'll discover it's very unlikely that it occurs at noon. It's going to be slightly different. And then with the difference in high noon, or whatever you want to call it, and noon, you can calculate what your longitude is, and that's what your assignment's going to be. I hope you have better weather than I had, so good luck. And next class, or next week when I see you again, we'll be looking at latitude. Okay, have fun.